We started with how to draw the main system. And we learned a lot about truss. After you draw your main system, we learned also how to calculate your dead load, your live load, your wind load. Using RISA 2D, we are able to determine what is the tensile or compressive force in each member. And we learned how to design tension member in truss. We have two situations to avoid yielding, to avoid fracture. 0.9 F yield area gross, 0.75 I think F ultimate area effective. We need to satisfy both of them. In the same type of structure, we have another member under compression. This member, we need to design it just your design or your design compressive strength equal phi F critical area gross. That's all. Your design compressive strength equals this number. That means the force in your member, which called P ultimate from RISA must be smaller than or equal this value, phi F critical area gross. Anybody remember where we can get F critical? We have two options. We can use table or we can use some equations. We like tables. It's very easy. So right now we can design all members in your truss because all members, one of them under tension, one of them under compression. That's all. We learned also how to design a column. This one is a column. This element in your truss is column. And you are able, using RISA, to get your reaction or your normal force in this member. Your normal force on your column called P ultimate, which is coming from your combination. It's a very simple combination, 1.2 dead load plus 1.6 life load. If you don't have anything else, dead load and life load. We learned a little bit about this column also related to member under compression. Your reaction or your normal compressive force in the column from RISA or from structure analysis must be smaller than or equal phi F critical area gross. The only difference between column and member in compression, all members in truss, most of them double angle or single angle, as you like. But if you are designing a column like this one, your cross section most of the time is W-shaped. The same steps in design, but we selected another type of cross section. For truss, we are using angle or double angle. Most of the time, equal length. 6 times 6, 8 times 8, 4 times 4. For column, we are using most of the time W shape. So, if you would like to understand what is the relation here, we will discuss it in details in connection, but at the meantime, here is your column. W shape. At this location, we are welding something called gusset plate by welding. And from this gusset plate, you can expect your member with bolts, and maybe we have another member here, and this member is connected here, so we don't have intersection. Something like this. For this connection. We will talk about this connection in more details. How many bolts do you need? What is the final shape of your connection? All of this stuff we will discuss it in more details. So right now we design member under tension, member under compression, and your column under axial compressive force. Any question so far? Any question? And we started the story from scratch. We started the story from the beginning. First, we need to decide which main system. What is your layout? What is the applied force? Then structure analysis to get your results. Then your results will be compared to your design. Your tension force from RISA must be smaller than or equal your tensile compressive strength, your design compressive strength, your design compressive strength. Today we will talk about another element which called beams. Anybody here remember where is the beam in this layout? Do you have beams? Yeah, Berlin. Between this main system and the next main system, we have something in between this element called purlins. These purlins looks like a beam. So today we will start to analysis and the design of beams. We will talk about it in general, then more specific on purlins. Beams is horizontal element between columns. We have vertical column. In between we have beams. Sometimes your beam is main beam, main girder, which is supported by column directly. Sometimes we have another type of beam called secondary beam, like this beam, which is supported here on another beam and supported there on another beam. So all of them called beam, but this beam called secondary beam, your load on this beam is very small, but on this beam, main girder is very high. If you are talking about design of beams, we have two things we need to consider. The first one, flexure. The second one, shear. Go back to structure analysis. Do you remember chapter of beams? If you have applied load. Do you remember? We have two main diagrams we need to draw. The first one called shear force diagram. The second one called bending moment diagram. So your beam must support your bending moment, which called flexure, and your shear force. So if you are talking about design of beam, we need to satisfy the applied moment and the applied shear. So we have two steps for design. Commonly, cross-section used in beam, W or S shape, or I-beam. Sometimes your I-beam called W shape, sometimes called S shape, standard American cross-section. Design of beam in steel is very simple, very simple. Your applied moment from load, from RISA, from structure analysis, must be smaller than or equal phi bending time nominal moment. This term called design bending strength or design moment strength. Remember, without phi, without fail, your term Mn called, anybody remember?
Nominal.
Nominal, yes. Nominal means without any factor of safety, theoretical. Actually, we need some factor of safety. As you see, the collapse happened in this bridge just after construction, without any use, with no live load, no moving load, just on weight of the beam, collapse happened. So we need factor of safety. Anyway, so M ultimate called factor maximum moment caused by the controlling load combination. M node nominal design moment, fail resistance factor for bending. In moment, in flexural for beams, this term equal 0.9, like concrete. Your nominal moment, Mn, equal something called M plastic, which called or equal F yield Zx. That's all. So Mn, nominal moment, equal F yield. We know F yield based on what type of steel. Zx called the plastic section modulus about the x-axis. We can get this value from table. If we go back to your tables, we have a new table called design of beam. W shape. Here you go. Zx. Based on what is the name of your cross section, you can get your Zx directly. Zx times F yield, you can get your nominal moment. Nominal moment times phi, which is 0.9, you can get your design moment. That's all. It's very simple in steel.
Dr. England,
Yeah.
where do you find the ZX on the first column?
First column.
The new table.
Did you get the right table?
It's W shaped, right?
No, not W shape. The W shape, you can get a table for W shape to get properties. And you can get W shape for design. We have two different tables. I uploaded both of them. The first one called W shape, the second one called design of beam.
Thank you.
Okay? So one of them can give you the section properties like area gross, like I, R, all of this stuff. There is another one can tell you what is the design of this member or this cross section. Let me explain something for you related to concrete. If you have very little load on your steel beam, your stress distribution on your cross section, something looks like this. Here is your neutral axis. One side we have compression, the other side we have tension. If your load increased more and more, your stress at this location. Anybody remember what is the name of this location? Extreme fibers. Extreme fibers means the top point and the lowest point. This stress will reach F yield. Your stress cannot exceed yielding stress. So if your load becomes higher and higher or bigger and bigger, your remaining cross section will be under yielding stress. If your load becomes bigger and bigger and bigger to reach maximum effect, the whole cross section yielded. One of them yielding under compression and the second part yielded under tension. So we would like to calculate what is the nominal moment, the maximum resistance for this cross section. That means the whole cross section under yielding, but one part yielded under compression, and the second part yielded under tension. In between, we have something called neutral axis. So, your stress, here is your cross section. Your stress at the top, compression stress, equal yielding stress for this part of your cross section. The second part of your cross section yielded also, but under tensile stress. If you are trying to get equivalent force for this stress block, which called C, and equivalent force for this block, which called T, and your cross section is in equilibrium, so this compressive force equals this tensile force. C equal T. C is your F yield times this area to get a volume. This area equal A divided 2, which called area under compression. So, and your T tension force equivalent to this stress block equal F yield, this value of stress, time this area, which is area under tension. If you would like to get your distance between this force and this force, this distance equal A. You can get it. If you do some calculation and get your M equal F yield times Z, which called M plastic. Plastic means the whole cross section reach yielding. This M plastic will be the same like Mn, nominal moment. This is the maximum. We cannot exceed this limit. Then if you add phi to Mn, you can get your design. So the key in designing beam in steel, this term, Zx